Capacitors are another example of a type of circuit element that we will encounter being combined in series and in parallel. Here's a group of capacitors that are combined in series. These capacitors have capacitances C1, C2, and so on. This group of capacitors combined in series could be said to be identical to a single capacitor with an equivalent capacitance given by this equation. If we have a group of capacitors combined in parallel, as shown here, then the behavior of this group of capacitors in parallel could be said to be identical to a single capacitor whose capacitance is given by this equation. We will now verify the claim that a group of capacitors in parallel with each other will behave identically to a single capacitor whose capacitance is the sum of the capacitances of the capacitors that are in parallel with each other. Just like before, we will consider two circuits. In one circuit, we will have a battery of voltage V that's connected to three capacitors in parallel, and the capacitances of these capacitors are C1, C2, and C3. The other circuit we will consider will be a battery of the same voltage V, and that battery is connected to a single capacitor whose capacitance is C equivalent. Just like before, the derivation we present here for three capacitors in parallel can be straightforwardly extended to any number of capacitors that are in parallel with each other. Again, our guiding principle is going to be that away from the three capacitors in parallel, the behavior of the top circuit should be identical to the behavior of this circuit away from the equivalent capacitor. In other words, if I were to cover up the three capacitors in parallel and the equivalent capacitor and show you the rest of the circuit, you should not be able to tell which circuit contains one equivalent capacitor and which circuit contains three capacitors in parallel. Namely, the amount of charge that evacuates the battery and accumulates on the three capacitors in parallel must be equal to the amount of charge that evacuates the battery and accumulates on the plates of the equivalent capacitor. So I could say that capacitor 1 will accumulate a charge Q1 on its plates, capacitor 2 will accumulate a charge Q2 on its plates, and capacitor 3 will accumulate a charge Q3 on its plates. In the lower circuit, the equivalent capacitor will accumulate an amount of charge Q total on its plates. In both cases, if we cover up the capacitors, you should see the same amount of charge leave the battery and accumulate on the capacitor or capacitors. So we could write that Q total is equal to Q1 plus Q2 plus Q3. Because these capacitors are connected to a battery, there will be a voltage drop across the capacitors. For the circuit containing the single equivalent capacitor, the voltage drop across that capacitor will be the same as the voltage of the battery. So there will be a voltage drop V. For the three capacitors in parallel, the voltage drop across each of these capacitors will also be V, the voltage of the battery, because we have circuit elements that are connected to a battery in parallel. And similar to our discussion when we considered resistors in parallel, the top plates of the capacitor are all directly connected to the positive terminal of the battery, and the bottom plates of these capacitors are all directly connected to the negative terminal of the battery. So I could say capacitor 1 will have a voltage V across its plates, capacitor 2 and capacitor 3 will also have a voltage V across its plates. Because I could always write Q is equal to CV, I could write Q total as being equal to C equivalent for my capacitors in parallel times V, and I could write that as being equal to C1 times V plus C2 times V plus C3 times V. Now I could factor out the V's on the right-hand side of this equation, and I would get C equivalent in parallel times V is equal to C1 plus C2 plus C3 times V. And then when I cross out the V's, I end up with this relationship between the capacitance of the equivalent capacitor and the capacitances of these three capacitors in parallel. At this point, we have finished our proof that the equivalent capacitance of three capacitors in parallel is given as C1 plus C2 plus C3. However, there is another way we could go about proving this relationship. It seems reasonable to expect that if I have three capacitors that are in parallel, then if I were to push these capacitors together so that the plates are touching each other, the total surface area of that new capacitor would be equal to the sum of the surface areas of the three capacitors that I have pushed together. This suggests that we would expect C equivalent to be the sum of the capacitances. But this in itself is not a proof, because what if the distance between the capacitor plates is going to be different for these three capacitors? To go about proving this in a separate way, let us consider three parallel plate capacitors. We will assume that capacitor number 1 has plates of surface area A1 and distance between the plates D1, and therefore the capacitance of capacitor number 1 will be epsilon naught times A1 over D1. Similarly, capacitor number 2 will have plates of surface area A2 and a distance between the plates D2. Therefore, capacitor number 2 will have capacitance epsilon naught A2 over D2, and capacitor number 3 will have a capacitance given as epsilon naught A3 over D3. The key to this proof is going to be to recognize that if I have a capacitor whose capacitance is epsilon naught A over D, and if I double the surface area of the plates and double the distance between the plates, the capacitance of that capacitor will remain unchanged. We will first ask the question, by what factor do we need to change the distance between the plates of capacitor number 2 until that distance is equal to the distance between the plates of capacitor number 1? If we say that we need to change the distance between the plates of capacitor 2 by a factor of x until that distance is equal to d1, then that implies that I could write d1 is equal to x times d2. For example, if the distance between the plates of capacitor number 1 is 4 times greater than the distance between the plates of capacitor number 2, I need to multiply d2 by 4 to have that be equal to d1. Similarly, if I have to change the distance d3 by a factor of y until this distance is equal to the distance between the plates of capacitor number 1, I could write d1 is equal to y times d3. As we said up here, if we change the distance between the capacitor plates by a certain factor, and we change the surface area of those plates by that same factor, we will not change the capacitance. So I could write that C1 is equal to epsilon naught times A1 over D1. I could write C2 is equal to epsilon naught x times A2 over x times D2. And I could write C3 is equal to epsilon naught y times A3 over y times D3. Because we have said that d1 is equal to x times d2 and d1 is equal to y times d3, we could write the capacitance of capacitors 2 and 3 as being equal to epsilon naught xa2 over d1 and epsilon naught ya3 over d1. Now we will imagine that we take these three capacitors, capacitor number 1 as it is, capacitors 2 and 3 whose surface areas and distances have been appropriately scaled by the factors x and y, and we will push these three capacitors together to form one larger capacitor. When we push these three capacitors together, they all have a separation between their plates of d1, but the surface area of these three capacitors are going to be a1, x times a2, and y times a3. So the total surface area of my new larger capacitor is going to be a1 plus x times a2 plus y times a3. I could therefore say that the capacitance of this new capacitor is going to be given as C equivalent is equal to epsilon naught times the total surface area of this new capacitor, which is a1 plus x a2 plus y a3. And we'll divide that by the distance between the plates of this new capacitor, which is d1. Now we could take this equation and divide up the terms in the fraction. So I could write that C equivalent is going to be equal to epsilon naught a1 over d1 plus epsilon naught x a2 over d1 plus epsilon naught y a3 over d1. We could then write this as C equivalent is equal to epsilon naught A1 over D1 plus epsilon naught XA2 over X D2, since D1 is equal to X times D2, plus epsilon naught YA3 over Y times D3. When I then cancel out the x's in the second term and the y's in the third term, I will be left with C equivalent is equal to epsilon naught A1 over D1 plus epsilon naught A2 over D2 plus epsilon naught A3 over D3. So then this will give me C equivalent is equal to C1 plus C2 plus C3. Let's think about what we have done here. We began with three capacitors that are in parallel with each other, but we made no assumption about the surface area of the plates or the distance between the plates. We then scaled the distances of the plates appropriately to ensure that the distance between all the plates of these three capacitors was identical. And then we scaled the surface areas similarly so that the capacitances themselves would remain unchanged. We then pushed these capacitors together to create a single equivalent capacitor. The amount of charge that would accumulate on these three individual capacitors should be equal to the amount of charge that accumulates on the single equivalent capacitor. Then we demonstrated through some algebra that the equivalent capacitance of these three capacitors combined in parallel could be said to be equal to the sum of their capacitances. We will conclude the derivations in this chapter by considering three capacitors that are in series with each other and demonstrate that these capacitors will behave identically to a single capacitor whose capacitance is described by this relationship. Just like the other derivations we have presented, this derivation could be straightforwardly extended to any number of capacitors in series. I have intentionally left some room between the capacitor plates and between the labels C1, C2, and C3 and the capacitors because I will need to draw between them. Let us first consider the three capacitors that are in series with each other. Because these three capacitors are connected to a battery, there will be a voltage drop across these three capacitors. I will say that there will be a voltage drop of V1 across capacitor number 1, there will be a voltage drop of V2 across capacitor number 2, and there will be a voltage drop of V3 across capacitor number 3. The sum of these three voltage drops should be equal to the voltage of the battery. For my single equivalent capacitor, because this capacitor is the only circuit element I have other than the battery for this circuit, I could say that the voltage drop across this equivalent capacitor will be the same as the voltage of the battery. Therefore, I could write V, the voltage of the battery, will be equal to the sum of these three voltage drops, V1 plus V2 plus V3. Let's now consider the charge that accumulates on the plates of these capacitors. I could say that this equivalent capacitor will have a charge of plus Q and minus Q accumulate on its two plates. So we will say this plate on the left accumulates a charge of plus Q and the plate on the right accumulates a charge of minus Q. I am now going to claim that the plates of the capacitors in series will also accumulate a charge of plus Q and minus Q on their plates. So that means capacitor C1 will accumulate a charge of plus Q on the left plate and minus Q on the right plate. Capacitor C2 will accumulate a charge of plus Q on the left plate and minus Q on the right plate. And capacitor C3 will accumulate a charge of plus Q on the left plate and minus Q on the right plate. So how might we justify our claim that the charge on each capacitor in these two circuits will be the same? Let us first recall how we described capacitors. Our first description of a capacitor was two large parallel metal plates that are very close together. I could imagine that if I would take a box and enclose the right plate of capacitor number 1, the left plate of capacitor number 2, and the wire connecting these two plates together, the total charge inside this box is going to be 0. Q inside is equal to 0. To help us see this, let's imagine that this circuit is just floating somewhere in space. We have a battery, And the positive terminal of this battery is connected to one side of a wire. The other side of that wire is connected to the left plate of capacitor 1. The right plate of capacitor 1 is physically disconnected from the left plate of capacitor 1. The right plate of capacitor 1 is connected to a wire which is connected to the left plate of capacitor 2. Again, the left plate of capacitor 2 is physically disconnected from the right plate of capacitor 2. The right plate capacitor 2 is connected to a wire which is connected to the left plate of capacitor 3. Everything within this box is physically disconnected from every other part of the circuit. The capacitor plates within this box could be described as two large metal plates, and they are connected by a wire. Overall, when this circuit is not connected, there will be no net charge inside the box. I can imagine that the positive and negative charges within this box are evenly distributed between the two plates. However, as soon as I connect this circuit, then there will be a certain amount of positive charge that flows onto the left plate of capacitor 1. The charge plus Q that accumulates on the left plate of capacitor 1 will attract an equal amount of negative charge minus Q to accumulate on the right plate of capacitor 1. Because a whole bunch of negative charges have moved to the right plate of capacitor 1, then the left plate of capacitor 2 will be left with a net charge of plus Q. This net charge of plus Q on the left plate of capacitor 2 will attract an equal amount of negative charge minus Q to accumulate on the right plate of capacitor 2. Again, because a whole bunch of negative charges have moved to the right plate of capacitor 2, the left plate of capacitor 3 will be left with an overall charge of plus Q on it. This plus Q charge on the left plate of capacitor 3 will attract an overall amount of charge of minus Q to accumulate on the right plate of capacitor 3. Remember that the total charge within this box is 0. Before I connect this circuit, positive and negative charges will be evenly distributed between these two plates of the capacitors inside this box. However, after I connect this circuit, negative charges will flow to the right plate of capacitor 1, and an equal amount of positive charge will be left over on the left plate of capacitor number 2. Because the behavior of these two circuits must be identical, in other words, how much charge evacuates the battery to accumulate on the capacitor plates, the amount of charge that accumulates on the three capacitor plates in these capacitors in series must be equal to the amount of charge that accumulates on the equivalent capacitor in this circuit. Using Q equals CV, I could rewrite this equation relating the voltage drop across the three capacitors to the voltage drop across the equivalent capacitor as Q over C equivalent is equal to Q over C1 plus Q over C2 plus Q over C3. Because Q is the same for each term in this equation, we could cross out all of the Q's, and what we're left with is this result that we originally claimed.